In the next few minutes, I want to tell you a little bit about the nature of scientific research. And you could think of this as an explanation of the scientific method. In any case, it's important to understand how scientific research works because it's a way of thinking. It shows how scientists understand our world and try to learn the truth about it. Most science begins with making many observations, and scientists are curious people, and they like to observe what's going on in their world and ask questions about it. For instance, they would ask, what is happening? Now, after they made a certain number of observations, they start asking questions about what they see, and these questions very often take the form of, what would happen if so-and-so happened, or what if such and such were true? I'll give you an example. What if the Earth was not the center of the universe? And this was actually the kind of question that Copernicus and Galileo asked. And it was a question people before them had not asked. Now, when you make questions like this, they very often lead to hypotheses. Now, what's a hypothesis? Well, a hypothesis is like an educated guess. And very often it takes the form of a statement that suggests that certain things should happen if you did such and such. For example, in the case of the sun that we just mentioned, if the sun were the center of our universe, then you ought to be able to predict certain patterns or phases of the planets that go around it. And actually, this is the way Galileo proved the idea that the Earth and the planets rotate around the sun. It's like you see with the moon. As it rotates, it has certain phases depending on how the sun shines on it. And Galileo made little diagrams, and he considered the different alternatives of how planets should look. He picked Jupiter to study because it's big and he had primitive telescopes back in those days. Scientists also like to pose their hypotheses in the form of alternatives so that no matter what you do in your experiment or no matter what the results are, you get some meaningful answer. And these hypotheses are often stated in the form of this should happen or that should happen or that should happen. And the nice thing about that is that no matter how the results turn out, they tell you something very useful. Then, of course, the next step is to test the hypothesis. And that involves designing an experiment and collecting the data carefully and interpreting it. And we'll have more to say about that in just another slide or two. Then you evaluate the results, of course, and you draw certain conclusions on the basis of those results. Well, the first thing that I'd like to emphasize is that good research is often hypothesis-driven. And sometimes even scientists forget that. To answer this question about why is that important or why is it true, we have to realize that if you have a hypothesis, then it makes certain predictions and it directs the way you design an experiment. If you don't have a hypothesis, then it's like going fishing. You throw your hook out and hope you catch something. And that's not very efficient. So I guess that's the main reason for having hypotheses, is that it makes your research more efficient. Well, let's say a few more things about what is a hypothesis. And as I said earlier, it can be an educated guess, but very often it's a lot more than an educated guess. And it's always based on something you think you know. And it can be a logical conclusion where you draw certain deductions from what you know. And this is an example of that is in the case of air pollution. You know that air pollution makes you cough and gag, okay? From that observation you might deduce that air pollution is irritating your lungs and the cells in your lungs. From that you might say, you might suggest that the cells in the lungs might be damaged by that. They might cause emphysema, or they might even end up becoming cancerous. So you can generate hypotheses and say that, well, air pollution might cause emphysema or lung cancer. And then, of course, you have to test that. Other hypotheses are developed by inductive thought. where you make sort of a grand synthesis. And this was the case, for example, in the case of Darwin's theory. He had a lot of observations and couldn't make deductions from them, but he could make a synthesis, and it led to the theory of evolution. This leads us to the next issue, and that is a good hypothesis ought to be testable by experiment. Well, of course, that's the problem with Darwin's theory of evolution. You can't test it because the timescales are so long. Same could be said for many of Einstein's theories until better methods came along where they could be tested. And then in any case, the experiment that you design in order to test a hypothesis should predict certain results. And if you get those results, it supports the hypothesis. And if you don't, then it, of course, puts the hypothesis into question. Well, let's take some examples here. Let's take the fact that we know that lead is a poison. So you might deductively conclude that, as a hypothesis, that other heavy metals might be toxic, metals like uranium, cadmium, and so on. So one way to test this hypothesis is to expose a group of animals to the different heavy metals, lead, another to cadmium, another to uranium, and so on. And then you would predict that if the hypothesis is correct, that one or more of these metals will prove to be toxic. So now let's consider a little bit about how to design an experiment. Experiment, of course, the purpose of an experiment is to test the hypothesis. And the key is to account for all the variables, or at least all the variables that you can think of that might influence the result. And you need a control group, and I'll say more about this in a minute. And you have to make sure that the tools or the methods you're using to perform the experiment are appropriate to the question that you're testing. Now, in the case of variables, in accounting for variables, you have to realize that what variables are factors or conditions that can change and influence the results. And of course, you want to keep all of the variables constant except the one being tested. In the case of our metal, you want only the metals to vary, use different metals. You also need a control for the variable under test. And actually, you may need several kinds of controls. Now, in the case of the metals example, you might want to have, for instance, a test group that doesn't get exposed to a metal. And these kinds of control groups are said to receive a placebo treatment. And then each of the other groups would get a different heavy metal exposure. There are also such things as positive and negative controls that we should talk about. A negative control is a test group in which, in this case, for instance, you might test a nonmetal, like say carbon. You might want to expose one group to carbon, and since it's not a metal, there's no reason to think it would be toxic, at least in comparison to these other metals that you are testing. And a positive control would be to test a metal that you know is toxic, like lead, for instance. Now, there are certain problems in this example I'm giving you, and they very often come up with other kinds of experiments. And that is that the different control, the different test groups may be toxic in different ways. In fact, let's take uranium as a case in point. Uranium is radioactive. And these other metals, like lead and cadmium and so forth, are not radioactive. So if you saw an effect in the uranium group, you don't know whether that's due to the fact that it's a heavy metal or the fact that it's radioactive. Now, another thing you have to do in designing experiments is to make sure you have an appropriate species to test. And of course, if you're interested in animals, you don't want to test plants. But more than that, even in the case of animals, you want to use a species that you know is sensitive to whatever it is you're testing, and yet appropriately sensitive. You don't want to pick a species that's super sensitive, and you don't want to pick one that is sub-sensitive. You also have to identify appropriate indications of sickness, here in the case of this metal experiment. What are the signs of sickness from metal toxicity? And you have to know what these are, and then you have to have ways to measure them in order to conduct this kind of experiment. And then there's this other issue that you have to have a meaningful range of doses. And it has to be over an appropriate time of exposure. You know, maybe a metal is not toxic if you take it every day for a couple of days. But if you were exposed to it for several months, then it might become toxic. So you have to keep all of these things in mind. Now this curve, by the way, makes another point about the concentration or dose of substance that you expose animals to. And this curve, or bar graph, which if you draw a curve from the tops of the peaks, produces a curve, is typical in biological systems. And what it shows on this vertical axis is percent of response, and on the horizontal axis it's showing dose or concentration. This is sort of a generic kind of graph. And what it shows is that there's a certain range of doses that are that are low enough that they have very little or no effect. And so if you were testing in this range of concentration, you might not see any effect, but you haven't proved anything either, because you weren't testing appropriate doses. A typical response produces a curve that's sort of S-shaped, like the letter S. And the reason it does is in part that at high concentrations you've reached a ceiling. You can't get any more toxic than this. You know, this is the maximum effect that you can get, and it levels off, and therefore you've created what you might call a ceiling effect. Whereas down here at these very low doses you may have a basement effect. You can't get lower than zero. Well, of course, the next thing of importance is to do the experiment. You know, after you've designed it and you've set up your control groups and you've got appropriate species, appropriate methods, appropriate ranges of concentrations or doses, then you actually have to do the experiment where you collect the data. One thing I've noticed about a lot of my students who do research is that they don't take the experiment seriously enough. They don't realize that an experiment is like a big ball game. You've got to get up for it. You've got to be alert and pay attention to what's going on, because for one thing, things very often go wrong. You know, your instrument doesn't work just right, or you see a result in process that might cause you to rethink the whole issue and, you know, redesign the experiment and so forth. And so the experiment itself is the time when you have to be especially alert to make sure that you know what's happening and that the data you collect are good, that they're clean. You can believe these results because, of course, you're going to base your conclusions on these results, on the data. So let's assume now that you've got the experiment completed and you've got the results in front of you, and now, of course, is the problem of interpreting what these results mean. And the first thing you have to realize is that whatever the results are, they may be misleading. They can either be falsely negative or they can be falsely positive. And of course that is a question that you've got to get resolved before you can be sure how to interpret these results. And now listed here in this slide are at least 6 different reasons why you could get misleading results, and it relates to things like you know, your choice of species, or the route of exposure you used, or the symptoms you measured that were signs of sickness, and of course the dose and the time of exposure of the substance. And there could also be statistical problems. You know, maybe you didn't have a representative sample of animals, maybe you didn't have enough animals, and so on. Well, this brings up what you might call a general rule in science, and that is that whatever results you get, before anybody can really believe it, they have to be replicated. The experiment needs to be done again, preferably by somebody else in another laboratory. and you should get similar results. Now, of course, sometimes it happens that you don't get similar results, and that is sometimes a growth opportunity for discovery when you try to examine why you could not replicate the original experiment. And sometimes important discoveries are made that way. The results have to be displayed and communicated in ways that make them easy to understand, and this usually involves making data tables or maps or graphs and charts, visual methods for presenting the results so that other people can understand them and make conclusions from it. This business of making conclusions brings us to this slide, which emphasizes that there are certain errors that are common in interpreting research data. And the first one probably is this business about confusing correlation and causation. I'll give you an example. Everybody knows that rain and lightning go together, but neither causes the other. They're both caused by something else. And you always have to keep that in mind when you interpret research results. Another common error is that the investigator gets so focused on his hypothesis and what he's looking to happen that he fails to consider alternative explanations. You know, there may be explanations and possibilities that never entered into the generation of the hypothesis, and he sort of has blinders on because of that. And then another common failure is to get so excited about your results that you think it applies to everything. You know, you generalize it too much. How you interpret research results is important because it leads to conclusions. And these conclusions in science lead to decisions. They may be decisions by scientists, or they may be decisions by public policy makers or public health people or whatever. So the interpretation has to be done very, very carefully. And of course, the most important point is that the decisions have to be made on the basis of the evidence. What does the data show? Your decisions and your conclusions should be based on what happened, not on what you hoped for, or what you wanted, or what you thought should happen, but what actually happened. In other words, scientists go where the data take them. And sometimes the data take you places you didn't want to go. And they may cause you to rethink your whole approach to the subject and throw away your hypothesis and start over again. Well, this, of course, leads to a lot of consequences for scientific evidence. But the important thing to emphasize is that the decisions you make about science are based on evidence, and that this evidence governs what we end up believing and the values we place on the research findings. And it affects our value systems in many ways. It can be technical details of what we value in research, you know, what's a good method to use and things of that sort. Or it can be more philosophical, like, you know, how scientists view the theory of evolution, for instance. Those are value judgments, and they are almost inevitable as a consequence of research. All research leads to the future, points to the future, because the results you get, whatever they are, very typically lead to new questions. And these questions make you, force you to make decisions about what are we going to do next? What follow-up measures do we have to take? And what kinds of new hypotheses do we need? And so the point is this, that science is a never-ending process. And it's a quest, really, to understand our world and ourselves.